Welcome back to bilingual e-lectures for diploma students on civil engineering subject structural engineering in unit 5. This is lecture 5 on the topic simple beams and welded connections. And beams are subjected to transverse loads generated from the floor slab or any other masonry works. And these loads cause bending moment and shear force on the beams. Beams may also be subjected to torsional moment when the transverse loads act at an eccentricity to the longitudinal axis, and also it experiences axial forces when it is provided at an inclination. So, beams are subjected to shear forces and bending moments, torsional moments and axial forces as the case may be. In general, beams are subjected to shear forces and bending moments, and the definition for beams of course is this, and smaller size of beams are used to take care of the roof loads are called as joists, and a greater size of a beam which is used to take care of the loads of the joists, multiple number of joists, or a multiple number of joists are supported by means of a girder. So, this is also a type of a beam. And again a purlin is a member which take care of the roof load and in the steel roof trusses. And again a lintel, it is a small sectional size of a beam which is provided over the openings, internal as well as external openings, maybe the door opening or the ventilator opening or the windows opening, etc. And these beams are to be designed for the strength requirements and the serviceability requirements, namely deflection limitations as stipulated in section 8 of table 6 of IS 800/2007. And classification of steel beams: simple beams are nothing but the rolled sections in general, and rolled sections again the I sections, channel sections and T sections, and they are used to take care of, or they are used to resist a simple bending. And the other form of simple beams are the built up sections or the compound beams, in which two or more than two rolled sections are used to fabricate and as a single unit, and this will take care of all these bending moments. And the connection between the two rolled sections and the extra cover plates at top and bottom or by means of welding or by means of riveting or by means of bolt and nuts. And the other form of simple beams are the hollow sections, maybe of rectangular section or maybe of circular section with sufficient thickness of the walls. And these are all the images of plate girders and the box girders, latticed girders. Latticed girders are the girders which are fabricated by bracing the bars at the web portion. The flanges of such beams will be of channel, angles or T's. And the other classification of beams depending on the lateral support. Lateral restraints are provided for the compression flanges to avoid the lateral buckling of flanges, so that the beams fail by yielding, and these types of beams are called as laterally supported beams. In general, laterally supported beams are preferable than the laterally unsupported beams. The other classification is laterally unsupported beams. When the compression flange of a beam is not supported in the lateral direction, then there is a possibility of lateral buckling. So, with this lateral buckling, the material in the cross section fail before it attains the yield strength or before it attains the its capacity. So, that is the disadvantage of laterally unsupported beams. And sections, of course, classification of sections, it is based on the width to thickness ratio, that is geometrical property, and main important is sections which are capable of forming plastic hinges and capable of or having the rotation capacity before its failure is known as plastic sections. or class 1 sections. Similarly, other type of sections of course that we have seen in chapter 2 of compression members are class 2 or compact sections, class 3 or semi compact sections, and class 4 or slender sections. Effective span and minimum web thickness of the members. In the case of laterally supported beams, the distance between the centers of support shall be taken as effective span, and in the case of laterally unsupported beams, the effective length of lateral buckling is determined from the table 15 and 16 of IS 800 2007 depending on the conditions of the restraints. And very important parameter for the beams or design of beams is the web thickness. The section resisting bending moment and shear force will be fully effective only when the web is not susceptible to shear buckling before the process of yielding of flanges. And the code specifies the ratio of depth to thickness of the web, depth of web to the thickness of web shall be less than or equal to 67 epsilon, where epsilon is the yield stress ratio which is given by an expression 250 by Fy whole square root. And for sections with slender webs which are susceptible to buckling before yielding, the flanges may be assumed to resist the bending moment and the web to resist shear force only. Maximum deflections permitted for the simple beams. The values of maximum deflection is simply supported and cantilever beams are different for different loading conditions are listed now. For simply supported beam with UDL, the maximum deflection permitted is 5 by 384 WL power 4 by EI, and for the same simply supported beam, if it is of central point load carrying central point load, the maximum deflection is PLQ by 48 EI, and for the cantilever with the UDL it is WL power 4 by 8 EI, and the cantilever with the point load at free end it is PLQ by 3 EI. In the case of laterally unsupported beams, the compression flanges may undergo lateral buckling. So, this has to be checked for the lateral buckling, and the more important or most important property while designing a steel beam or the elastic moment of resistance and plastic moment of resistance. And of course, elastic moment of resistance we have seen in unit 2, 3, 4 etc. in RCC structures. It is nothing but the moment carrying capacity of the section when the bending stress at the extreme fiber alone just reaches its yield stress value. So, that is elastic moment of resistance. Plastic moment of resistance on the other hand, it is a moment resisting capacity of the section when the bending stress reaches the yield stress value all over the section. So, that is plastic moment of resistance. So, the main difference between the elastic moment of resistance and the plastic moment of resistance is this: beam cross section la extreme fiber la yield stress reach ஆயிருந்த அப்போ அதனோட moment resisting capacity என்னவோ அதுக்கு பேர் வந்து elastic moment of resistance. அதே beam ஓட cross section la full area yielding stress ல attain ஆயிருக்கு அப்படினு சொன்னால் அந்த சமயத்துல என்ன அதுக்கு resistance கொடுக்கிறதோ that is plastic moment of resistance. So, ஞாபகம் வச்சுக்க வேண்டிய பாயிண்ட் என்னன்னா எலாஸ்டிக் மொமெண்ட் ஆஃப் ரெசிஸ்டன்ஸ்ங்கிறது வந்து எக்ஸ்ட்ரீம் ஃபைபரில் மட்டும் ஈல்டு ஸ்ட்ரெஸ் ரீச் ஆகிருக்கும், அது அப்போ என்ன ரெசிஸ்ட் பண்ணுறதோ அதுதான் எலாஸ்டிக் மொமெண்ட் ஆஃப் ரெசிஸ்டன்ஸ். பிளாஸ்டிக் மொமெண்ட் ஆஃப் ரெசிஸ்டன்ஸுங்கிறது வந்து எல்லா ஃபுல் ஏரியாவுமே ஈல்டு ஸ்ட்ரெஸ்ஸில் வந்திருக்கும், அப்போ என்ன மொமெண்ட் ரெசிஸ்ட் பண்ணுறதோ அதுதான் பிளாஸ்டிக் மொமெண்ட் ஆஃப் ரெசிஸ்டன்ஸ். அண்ட் த அதர் ஜியோமெட்ரிக்கல் ப்ராப்பர்ட்டி elastic section modulus. Of course, elastic section modulus is given by ratio between elastic moment and the yield stress, that is Ze is equal to Me by Fy, and plastic section modulus is denoted by Z suffix p Zp, and that is the ratio between the plastic moment and the yield stress, that is Zp is equal to Mp by Fy. And the basic design principles which are involved in the designing of steel beams are these: 1. The primary actions on the steel beams are bending moments and the shear forces, and for the design purpose, when the design shear force of the section is less than or equal to 0.6 times of the design shear strength of the section, then the entire cross section may be assumed as fully effective in resisting the bending. On the other hand, second part, when the design shear force in the section exceeds 60%, that is 0.6 times of the section's design shear strength, then the section has to be designed for the combined effect of bending and shear in accordance with the provisions given in IS 800/2007. In this case, reduced moment capacity is taken as the design bending strength of the section, and this chapter deals with design of simple beams, design shear force less than 0.6 times of the design shear strength of the section. Then that means we are going to see the design of simple steel beams which are fully effective in resisting the bending moment. And design strength in the bending for laterally supported beams, I repeat, laterally supported means that will fail by yielding of cross section, or the torsional buckling will not occur in the lateral supported beams. These are the two keywords one have to bear in their mind while designing the laterally supported beams. And the condition to be satisfied for the design of simple beams, if the entire cross section is assumed to be effective in resisting the bending moment, is this, that is, when the design shear force V is less than or equal to is missing here, equal to V is when V, that is the design shear force is less than or equal to 60% of the design strength of the given section, then the bending strength of the section is given by an expression MD is equal to beta B into ZP into Fy by gamma m naught. Again the bending strength is governed by one geometrical property and one mechanical property. Here the geometrical property is the plastic section modulus denoted by Zp, and the mechanical property is denoted by Fy. Of course, the Fy yield strength is always associated with the partial safety factor for the material in yielding gamma m naught. So, these two are the mechanical property of the material, and this is the geometrical property Zp, and of course, this is a factor which is multiplied with the geometrical property, and that is 1 for plastic and compact sections, and it is nothing but the ratio between the elastic section modulus and the plastic section modulus. So, the point you have to remember is this: bending strength is the product of a geometrical property and a mechanical property. Here the geometrical property is the section modulus or plastic section modulus, and the mechanical property is the yield stress, and of course, yield stress is associated with always the partial safety factor gamma m naught, and all these things to be multiplied by a factor which is nothing but the ratio between the elastic section modulus and the plastic section modulus. Now, and this is to be restricted to a expression or a value which is given by the code in the code. So, MD max is equal to, or design bending strength maximum or restricted is equal to 1.2 times of Ze Fy by gamma m naught for simply supported beams, and 1.5 times of Ze Fy by gamma m naught for cantilever beams. When the design shear force exceeds 60% of the design shear strength of the section, then the section is to be designed for the moment as well as shear. So, in that case, the reduced moment capacity is to be found by using the expression MdV is equal to Md minus beta times of Md minus Mfd, which should be less than or equal to 1.2 times of Ze Fy by gamma m naught for plastic and compact sections. So, in this chapter we are going to deal with the design of simple beams for the case A, that is when the design shear force is less than 60% of the design shear strength of the section. So, we will take up the other part of the design, that is the design shear strength of the section. When the thickness of web is greater than or equal to d by 67 epsilon, then the design shear strength of the cross section is given by V d is equal to V n by gamma m naught, where V n is the nominal shear strength of the cross section and it is given by an expression A v into F y w by 1.1 times of root 3. Again A v is a area in shear and F y w is the yield strength of the web, and 1.1 root 3 is a partial safety factor for the yield strength of the material. In the case of thin web, that is thickness of web is less than d by 67 epsilon, the nominal shear strength is given by the shear strength of the web, which has to be determined as given in the code IS 800/2007. And now the design procedure to design a simple steel beam. Find the design bending moment at the critical section, and number 2, find the approximate plastic section modulus required by using the expression 1.1 into m divided by F y, and with the value of plastic section modulus arrived, select a suitable section, or you can choose 2 or more 3 sections. While selecting the section, the depth of the section should be greater than span by 220 to satisfy the stiffness requirement. This is very important. And next step is to check whether the section is susceptible for web buckling. Then that means to avoid shear buckling, the condition is thickness of web should be greater than or equal to the depth divided by 67 epsilon. And the fifth step is to check or find the class of the cross section selected. Class in the sense or classification of the section selected, class 1, class 2, class 3 and class 4, that is plastic, compact, semi compact and slender, and by referring the table 2 of IS 800/2007. And next step is to find the design shear strength at the section considered, and this design shear strength is compared with the design shear force. If this design shear force is less than 0.6 times the design shear strength of the selected section, the section selected is OK. And for that section we have to find out the moment carrying capacity or design bending strength capacity by using the expression m d is equal to beta b into z p into f y by gamma m naught, which is to be restricted to the value of 1.2 times of z e f y by gamma m naught for simply supported beams and 1.5 times of z e f y gamma divided by gamma m naught for cantilever beams. And if V by V d is greater than 0.6, section with a larger depth or greater thickness of web may be tried. Otherwise, the section is to be designed for combined effect of shear and bending. Shear S is missing here, to type here. The design bending strength is greater than the design bending moment at the section. The section selected is safe against limit state of collapse in flexure, and we have to check that for the maximum deflection with the limiting values given in the code. We will work out one problem on this design of simple beams, and this example. Determine the design bending strength of ISLB 400 at 569 Newton per meter, assuming it as a plastic section, and yield stress is given here. It is used as a laterally restrained simply supported beam for an effective span of 6 meters. We are asked to find out the design bending strength of the given Indian standard lightweight beam designated by its depth 400 and its self weight 569 Newton per meter. Also we are given a clue that we have to assume the section as a plastic section. Now, these are the data given. Assuming the given section as plastic section, first step is to write down the properties of the given section, rolled section, from the steel table. So, it is very important for the students. Once you open the steel table, you write down the required properties at a time. So, for ISLB 400, I at the rate of 569 Newton per meter by referring the table. Gross area is found to be 7243 millimeter square, HRD is 400 mm, breadth of the flange is 165, thickness of the flange 12.5 mm, thickness of web 8 mm, and the geometrical property of the section IZZ, that is 193.063 into 10 power 6 mm power 4, elastic section modulus and plastic section modulus. So, all these properties you have to take the value from the steel tables. Second step is to classify the selected or given section, cross section. In this we are going to classify the cross section based on its limiting width to thickness ratio, and for this we have to refer table 2 of IS 800 2007. So, the height of webs, this is the total depth of the total depth. From the total depth from this point to this point, deduct the thickness of the flange. So, that comes around 375 mm, this is the depth of the web or height of the web alone, and width of outstanding element, this is the width of outstanding element from this point to this point we have to measure. This is given in the code, illustrated in the code. So, breadth of the flange or breadth of the outstanding element is measured from this point to this point, therefore, it is 165 by 2. So, that comes around 82.5 millimeter, and this is a yield stress ratio, epsilon is equal to 250 by Fy the whole square root, and for plastic section, that is class 1 section, the limitation is 9.4 epsilon. So, 9.4 epsilon value is 9.4 and the B by Tf value is 6.6. Since the breadth to thickness ratio is less than the value given in the code 9.4 epsilon for class 1 section, the section is classified as class 1 section or plastic section. And limiting depth to thickness web, for web buckling we have to check this ratio, that is the ratio between depth to the thickness of the web. Here we have to take the depth 375 and the thickness is 8. So, it comes around 46.875, which is less than the 67 epsilon. Therefore, the section is safe against web buckling. And now, the third step is to find out the design bending strength, and beta B value for the plastic section is 1, and the expression to be used to find the design bending strength is MD is equal to ZP into Fy by gamma m naught, where ZP is this value and Fy is this value, gamma m naught of course this value, and the bending strength is found to be 249.87 kilonewton meter. So, I repeat, first you write down the properties of the section from the steel table. Second, you classify the given cross section, class 1, class 2, class 3 or class 4, and you check whether the web is susceptible for web buckling. If it is not so, then we go in for the design strength, third step. It is a simple expression, MD is equal to ZP into Fy by gamma m naught, and we have arrived at the design bending strength of the given ISLB as 249.875 kilonewton meter. And second example, this is an ISLB 450 at 653 Newton per meter, which is used as a laterally restrained simply supported beam for an effective span of 6 meter. And here, apart from the design bending strength of the section, we are asked to find out the maximum UDL it can carry in addition to its self weight, and the mechanical property of the section is given, yield stress is 300 megapascals, and the deflection at the midspan, the condition given here is it should not exceed 20 mm, and the mechanical property Young's modulus is given as 2 into 10 power 5 Newton per millimeter square, and these are the data given. first step is to write down the properties from the steel table. So, these are the properties of the given ISLB 450 at 653 Newton per meter, and second step is to classify the given cross section. This is height of the web and width of outstanding element, yield stress, and this is the yield stress ratio. So, limiting width to thickness ratio is found to be 6.34, and for class 1 this is to be within the limit of 9.4 epsilon, that comes around 8.58. So, since the B by Tf value is less than 9.4 epsilon, the section is class 1 section or plastic section, and ratio between depth to thickness of web is equal to 49.21, which is less than 67 epsilon. So, the section is not subjected to web buckling before yielding. And third step, design bending strength. For plate section, it is not plate section, actually it should have been written as plastic section. For plastic section, beta B value is 1, plastic section beta B value is 1, and the design bending strength, substituting the relevant values, the design bending strength is found to be 382.19 kilonewton meter. இந்த பெண்டிங் ஸ்ட்ரெங்த்தை வந்து எதோட நம்ம கம்பேர் பண்ண வேண்டியதாக இருக்கும்னா அதிகபட்ச பெண்டிங் மொமெண்ட் ரெசிஸ்டன்ட் ஆர் பெண்டிங் ஸ்ட்ரெங்த் கொடுத்துருக்க எக்ஸ்பிரஷன் என்னென்னா சிம்பிளி சப்போர்ட்டட் பீமுக்கு வந்து 1.2 டைம்ஸ் ஆஃப் ZE into Fi by gamma m naught. ஸோ இந்த எக்ஸ்பிரஷனில் சப்ஸ்டிடியூட் பண்ணி எவ்வளோ வேல்யூ வருதுன்னு பார்க்கணும். இதுதான் அதிகபட்ச பெண்டிங் ஸ்ட்ரெங்த்தாக இருக்கணும். ஸோ நமக்கு வரது 382.19 kilonewton meter, and the maximum is this value is to be restricted to this, and therefore the design bending strength is found to be 382.19 kilonewton meter. And second, the design shear strength of the section. So, shear area for the rolled section is H into TW. H is the total depth of the section, that is given here. This is the total depth of the section, and thickness of the web is this. So, total shear area is 3870 millimeter square, and since d by TW is less than 67 epsilon, the shear strength of the given section is found by Vd is equal to AV shear area into yield stress divided by the partial safety factor. So, that is given by this expression. Of course, the value is found to be 609.36 kilonewton, and the maximum UDL the beamman can carry is, with respect to bending strength, it is found to be, of course, the bending strength of the member or the section is 382.19 kilonewton meter, and the expression to find the bending strength of the member is WL square by 8, and from this design dead load is found to be 84.93 kilonewton meter. Safe load on the beam, by dividing the partial safety factor, it is found to be 56.621, and deducting the self weight of the beam, the safe imposed load on the beam with respect to the bending moment consideration is found to be 55.968 kilonewton per meter. And the other criteria to find the maximum UDL that could be carried by this beam is a stiffness. Stiffness, of course, it is measured by the deflection. Deflection or maximum permitted deflection for this case is 20 mm, it is given in the problem, and the theoretical deflection, of course, for a simply supported beam which carries a UDL throughout its span is given by this expression 5 by 384 into WL power 4 by EI. Substituting this 20 mm for this or equating these two, theoretical deflection as well as the limited deflection given in the problem, the design load is found to be 65.27 kilonewton per meter. I am sorry, it is not design load, it is a serviceability condition. So, it is a working load. So, 65.27 kilonewton per meter, and from this deducting the self weight of the beam, safe imposed load on the beam is found to be 64.618 kilonewton per meter. This is with respect to stiffness consideration. And the last one is the maximum load the beam could carry by the shear strength capacity, and the actual design shear force is given by this expression WL by 2 or dead load WD into L by 2, that is equal to 69.367 kilonewton, and equating these two, the design shear strength and the design shear force, the design shear force is found to be 203.122 kilonewton per meter, and dividing this value by partial safety factor, the safe imposed load on the beam is found to be 135.41 kilonewton per meter. And again, deducting the self weight of the beam, the safe imposed load on the beam is found to be 134.76 kilonewton per meter. First criteria, from the bending moment consideration, the safe imposed load is found to be 55.968 kilonewton per meter, and second condition, with respect to the stiffness, it is found to be 64.618 kilonewton per meter, and the third one is shear strength, it is found to be 134.76 kilonewton per meter, and the least of the above three values is to be taken as the maximum permitted load in the beam. And therefore, the sixth step answer is the maximum UDL the beam can carry in addition to its self weight is equal to 55.968 kilonewton per meter. To work out in the examination process, it is very important to by heart the steps involved in working out the problem. First step is to write down the properties, second is to classify the cross section, third one is the design bending strength, fourth one design shear strength. Then you can calculate the criteria given in the problem to find out the UDL, maximum UDL carrying capacity, to find maximum UDL carrying capacity, that is with respect to bending, with respect to stiffness and with respect to shear. So, that is how you have to work out these types of problems. Thank you for watching this video.